Hi, so today we'll be discussing the paper Efficient Streaming Language Models with Attention Sinks by folks from MIT, Meta, and CMU. So, what does this paper do? From their own GitHub repo, they deploy LLMs for infinite length inputs without sacrificing efficiency or performance. And if you see here, the left you have, so this approach is also called streaming LLM. So, without LLM on the left, without streaming LLM on the left, with streaming LLM on the right. After a while, this model's performance breaks and it also goes out of memory after a while the streaming LLM one just goes on and on and on. So they say that deploying LLMs in streaming applications such as multi-round dialogue, where long interactions are expected, is urgently needed but has some challenges. So this approach is for streaming applications, in which case like uh, you are talking to a chatbot and you want to keep on interacting with it for a long period of time. So if your model was trained on a fixed number of sequence lengths, say 4,000 tokens, you don't want to stop after 4,000 tokens. You want to keep on going on, and that is called streaming. Uh, so they develop an approach for it, which enables LLMs which were trained on a finite length to generalize to infinite sequence length without any fine tuning. So say if your model was trained on a sequence length of 4,000, this approach allows a model trained on 4,000 sequence length to work on infinite sequence length or on an input of any sequence length and without any fine tuning. So you don't have to fine tune the model as well. And they say that they were able to integrate this into popular LLMs like Llama, MPT, Falcon, Pythia to perform modeling up to 4 million tokens and more. So this is huge. These models were trained on much less sequence length and they scaled it up. They used this approach to use these models for a lot of tokens, like for 4 million tokens. And they do this by uh, observing and exploiting a phenomena called attention sink, which we'll come to later. Okay, so they say that when applying LLMs for infinite input streams, there are two main challenges. So first is the memory usage and increased latency. So if you are performing dense attention, in which case you are attending to all previous tokens, your complexity would be quadratic in the length of the sequence. So if you increase the sequence length a lot, say 4 million, it would explode. Other is that existing models have limited length extrapolation abilities. That is, their performance degrades when the sequence length goes beyond the sequence length during pre-training. So what they mean is that if your model was trained on sequences of length n, and then so this was train, and if you do inference on sequence length of 2n, then your model performance degrades. First of all, is it even possible to like take a model which was trained on n and use it on 2n? It is actually. I thought it is not, but it is the case because attention is a generic operation and you can apply it to any sequence length. So if you have multiple inputs and like this is what you trained on, and so this is n, and you want to apply it on 2n, there is no problem really, because what you do is just you have these matrices W key, WQ, and WV. You pass each of these through it, and then you calculate an attention score by softmax. There is nothing stopping you from like extending it in the architecture. You can do this without any changes. Yeah, if you are using some positional embeddings and those positional embeddings had a fixed sequence length parameter, that might be a problem. But there are positional embeddings which you can use which are not constrained by the length. So the alibi paper does something like that, and I think even the rotary embeddings You can just extend them. I'm not sure about rotary, but yeah, you can essentially just use this. You use some position embeddings which are designed so that you can extend the sequence length, right? But the problem is, if you do this, the performance degrades. So a vanilla dense attention has complexity t square, where t is the length of the sequence, and it has poor efficiency and also poor performance. Performance is measured by perplexity, and lower is better, higher is worse. So yeah, vanilla attention won't work. So even if you do length extrapolation, it will fail in performance as well as efficiency. Okay, so how can we fix this? So there is this approach called window attention to one of the ways to address the at least the performance. Sorry, at least the efficiency is window attention, in which you maintain a fixed size sliding window on the KV states of the most recent tokens, and also it ensures constant memory usage and decoding speed. The model collapses once the sequence length exceeds the cache size. So what they mean is, okay, let me take it, explain it with an example. X1, X2, 3, 4, 5, 6, 7, and X8. And suppose your sequence length is 3. So say when you are at 4 and you can text at this 3, you want you have to calculate the keys and values for x2, x3, and x4. But do you really need to calculate the value for x3? Because you have already done the processing for x3 in this window, and you already have the keys and values for this. So you actually only you can cache these values and like the previous values, and you can just keep calculate the the new keys and values for the new token. And in that case, you'll, instead of doing, like, if this context length is L, instead of doing L square for each token, you will just be doing for one token, so it would be L, and for a sequence length of T, it would be T of L, right? So this is the sliding window, this is the window attention approach, which has good performance, but which has good efficiency, but it has poor performance. And the reason for that is, say when you are at x8 and you are using the cached value of x6, say, this value of x6 was calculated using this context window, which had x4, x5, and x6. But now you're using this in this context window. So there is a mismatch, and this mismatch creates a performance degrade, basically. So yeah, this has good efficiency but poor performance or poor perplexity. Another strategy is sliding window with recomputation, in which case, when you are at x8, you essentially forget about all of the things which came before, and you do the entire attention calculation again, which would be quadratic. So this is T of L square, which has good perplexity, but it has poor performance. So poor efficiency, because it is O of T times L square. Their approach is best of the both worlds. You get linear complexity and also good perplexity, a good performance. So this is some empirical evidence for the same for different LLMs, Llama, Pythia, Falcon, and Beidi. As you increase the input length, if you see blue is dense attention. After you exceed the pre-training length of about 4000, the perplexity shoots up or the performance degrades. And for window attention, after you uh, reach the KV cache size and you like start evicting uh, tokens from the initial tokens from your cache, the performance degrades, whereas their approach in red keeps on performing. So why does this happen? They say that this happens because of a phenomena called attention sink, which is that a large amount of attention score is allocated to initial tokens, irrespective of their relevance to the language modeling task. So this is what they observe here. So if you see the attention, uh, for the first two layers, you'll get a decent attention pattern. So like all tokens have some locality. So this token is attending to its nearby tokens, and this token is attending to some nearby tokens. So it will help to see a row of this. So this means this row means this the 14th token is mostly attending to the nearby ones and not too much to the initial ones. But this is just the case for the initial layers, initial two layers. Afterwards, when you go, there's a discrepancy in which if you see this dark red line, it means that most of the attention score is being given to the 0th token. So for all tokens, even like the 14th or 15th token, most of the attention score is going in the uh, initial token. So this is sort of acting as a attention sink. Uh, this is the case for say layer 2, layer 9, 16, 23, 31. So the model heavily attends to the initial token. And the reason for this might be because of the softmax. Because the softmax requires the attention scores to sum up to 1. So when you apply softmax, all the attention scores have to sum up to 1. So even if the current query does not have a strong match in many previous tokens, the model still needs to allocate these unneeded attention values somewhere. And so what it means is that say the 14 token is there. We are doing attention with all the initial 14 tokens. Now it is possible that this 14 token is not matching much with most of these, but because the attention needs to sum up to 1, it will have to give corresponding values like high values. So what it learns to do is that if it is not matching much, uh, it learns to put a large part of the attention score to the initial token so that it sums up to 1. So x1, x2, x3, x4, x5, x6. So if you are at x6, it could be something like, so all of these will have some attention scores. Now say that this is not really matching with most of them, but even then the scores which is needed would need to sum up to 1. So it will do something like 0.9, then 0.01, 0.02, 0.03, 0.04, something like that. These have to sum up to 1. Maybe they are not, but these have to sum up to 1. And what it learns for different, and also for like other context lengths also, it will have to sum up to 1. So what hack the model learns is that to just give this first few tokens, not necessarily the first one, the first few tokens a very high attention score so that the sum can be 1. And the reason behind the initial tokens, like why is that the case that the initial tokens are the ones which are getting all the weight even if they are themselves not matching much, is because these initial tokens are visible to all the subsequent tokens, making them more readily trained to surpass attention things. So because if you have a context, so it is there in this window also, it is there in this window also, it is there in this window also, this window also, this window also, and all these windows. So these are the common tokens which are present in every attention calculation. And so the model learns a hack that since this token would be there in every time when I do an attention score, if I have to like sum things up to 1, I'll give this a high score and I'll give a less score to the other tokens based on how important they are. So this is sort of like a normalizing constant of sorts for the model. So I'll do the calculations and whatever is left I'll give to the first few tokens. And the problem is that if you are doing that windowed attention thing, you are evicting these tokens. So if you are evicting these tokens, that messes up the calculation, and that is why your performance degrades. And what their approach essentially does is that since we know that these initial few tokens are important, we'll preserve these tokens. We'll not evict these tokens. So if I am at x9, if I have to do this, use this window, I'll use this window, but I'll also use these two. So I'll use something like this and this. I'll not forget about these initial tokens which work as attention sinks. And in their case, they use initial 4 tokens. So they'll fix these 4 tokens. These 4 tokens are not going anywhere. Even if you are somewhere down the calculation and using a window here, you'll also use these 4 initial tokens because they work as attention sinks. So that is the TLDR of their paper, of their approach. Basically, they observe that there is this attention sink phenomena going on where the first few tokens have a high attention score. So we'll just preserve those tokens. So here they investigate that there are two possible explanations for this attention sink phenomena. Either their semantics are crucial, so like the first few tokens are semantically useful, or the model learns a bias towards their absolute position, like the fact that they are the initial tokens. Either they are semantically meaningful, like the meaning of those tokens are important, or their position is important. So to distinguish between these possibilities, what they did is that they replaced the first 4 tokens, whatever they were, with a line break token, which does not have actually any semantic meaning. They observed the same phenomena regardless. So even if we had just line break tokens in the initial part, they were getting the high attention scores, and also if you preserved those tokens, they uh, r- restored the model perplexity to a good level. So this means that the semantical value, so like even if you had a garbage token in the initial stages, just having those tokens at that position helps the model. So the model is biased towards the absolute position of those starting tokens rather than their semantic value. Okay, so this is again explaining why that is needed. This happens because the softmax needs to sum to 1, and so the model needs some place to dump all the unnecessary attention values. And why do they focus on the initial tokens rather than the other tokens? Because the initial tokens are visible in all context windows. And what they see is that the pre-trained LLMs uh, are trained to utilize multiple initial tokens as attention sinks rather than just one. So these models X1, okay, how many times should I make this? So yeah, X1, X2, all this. So just using X1 as a context window, as a attention sink won't help. What they see is that for these pre-trained models, you need around 4 initial tokens as attention sink. Using one or two of them won't help. But this is because you're using a pre-trained model and you are trying to integrate this approach into it. What they say is that uh, if you actually keep this attention sink phenomena in mind and you have a special token in the beginning, which is like the sync token, you can get away with using only one of this. So while pre-training, if you have this sync token, which is always there in the attention window. So even if when you are doing a calculation for this, you have this sync token as well. If you do this in pre-training itself, then you can get away with using only one of this. Only one token will act as a attention sync. But if you use a pre-trained model like Llama, which was not trained using this, then you will need around 4 initial tokens. So here they explain how they use this to do, like how they implemented this. It's not very like I'll it's not uh, so what they do is, one important point is that when determining the relative distance and adding position information to the tokens, it focuses on positions within the cache rather than the original text. So what they mean is that uh, when you are at x9, the positions won't be 7, 8, 9, and 0. The positions would be 0, 1, 2, and 3. So focus on the position within the cache, not the absolute position. And then they explain how they integrate this to different position embeddings like rope, alibi. But yeah, these are mostly implementation details. Then here they describe like how they can, if you integrate this attention sync approach into the pre-training itself, which I talked about, that initial sync token, then you can get away with like just having one token and get the similar performance. So yeah, here they see that here they showcase their approach, the validity of their approach. So if you like the perplexity for like very super long text, so like 4 million or 3 million, the perplexity remains stable. So the model performance doesn't degrade even if you like scale up the sequence up to millions. So their approach works. They also say that like having that sync token during pre-training has no negative impact on the model convergence and performance. So adding that sync token does not change the performance, the convergence. Uh, yeah, they also observe that their approach is like using their approach makes streaming much faster. So they achieve 22 times uh, speed up. But in this case, they compare it with the sliding with window with recomputation approach because that was the only baseline which had a similar performance to this approach, like perplexity, and this was T of L square, and their approach is T of L, so they have a 22x speed up, so their method is also fast. So yeah, that is mostly the paper on a high level. Overall, I think it's a very cool paper because it works really well, and it like you can just use integrate into different pre-trained models. So they have already integrated it into Llama, Python, sorry, Pythia, Falcon, and MPT. So yeah, the code is public. People are making demos out of it. So yeah, it's cool. Yeah, and they have a good FAQ section here. So one interesting thing is that they're not actually changing the context window. So if Llama 2 was pre-trained on 4096, then the max, so their context window is also 4096. So the context of the model does not really change. So it is not as if uh, you had a sequence of length 4 million, and when you are at like position 4 million, the model will remember something that happened at 2 million. That context won't transfer. So it is not that it does not mean that the context window has increased. Like the model has context about all the 4 million tokens. That is not the case. It will have a very local context. It will have context about the 4096 tokens around here only. It won't remember if there was a name which occurred in this 2 million position, it would have probably forgotten about this at the 4 millionth position, which is what they say here. While you can input a lengthy text, the model will only recognize the latest tokens. Thus, if a book is input, the streaming LLM would only summarize the concluding paragraphs, which might not be very insightful. So they neither expand the context window nor enhance their long-term memory. It just makes streaming faster. So it just makes like even with the local context, things can be T of L square. So their work is making that T of L without degrading the performance, the perplexity essentially. So it is not as if you magically like scaled Llama to have a context window of 4 million and it remembers what happened at 2 million position. That is not the case. It is just that you can now use Llama on a 4 million streaming in a streaming sense. Like you can keep on generating and generating with a local context and efficiently in a linear complexity instead of like a quadratic complexity. So in the context window size, not the length. Length is anyway linear. The total length is anyway linear. Anyway, yeah, that's it for the video. Thanks for watching.